All right, today we start a new chapter. This is chapter 3, which is all about probability. And so, as the start of any chapter, there's going to be a lot of definitions and a lot of new formula type things. So be sure that you are looking at that and taking good notes on it. So, first one says, a blank experiment is an action or trial through which specific results, counts, measurements, or responses are obtained. The result of a single trial in a probability experiment is called what? So this first one says a probability experiment. The result of that is called an outcome. The set of all possible outcomes is the sample space. And finally, an event is a subset of the sample space that may consist of one or more outcomes. So one more time, the probability experiment is the action or trial that you're going to take. A single result of that trial is called an outcome. All the possible outcomes is called the sample space, and an event is a subset of that sample space that may consist of one or more outcomes. So, example 1 says we want to identify the sample space. A survey consists of asking people for their blood types, A, O, A, B, and AB. Those are the 4 blood types, including whether they are Rh negative or Rh positive. So that's the 2 options that we have for all, that's all the options we have for blood type. So determine the number of outcomes and identify the sample space. So the sample space is used with brackets. And basically, because of this diagram, and oftentimes a diagram definitely helps, we can see that one answer would be O positive. So one outcome is O positive. The next outcome would be O negative. We would then have A positive and A negative. We would then have B positive and B negative. And we would have AB positive and AB negative. And those are all of our options for blood types. So our sample spaces, all of them. That's our sample space. How many outcomes we have? There are 8 outcomes. So now I can start asking questions about that, such as, how many people have positive blood type? Well, if we don't care about the AB, A, B, AB, or O, then there are 4 possible outcomes with positive blood type. So we can start talking about different events then that happen with those outcomes. So simple events are often represented by uppercase letters such as A, B, and C. An event that consists of a single outcome is called a single event. For instance, consider the probability experiment that consists of tossing a coin and rolling a 6-sided die. The event, tossing heads and rolling a 3, is a simple event and can be represented by, so we want heads and a 3. So if we look at our chart, this would be heads or tails. So this is the coin flip, heads or tails. This, 1 through 6, would be the die. Die is singular, the dice, by the way. So the event of tossing heads and rolling a 3 would look like H3. So again, this is one outcome, making it simple. In contrast, though, if I say tossing heads and rolling an even number, so heads with an even number, that would be head 2, head 4, or head 6. So H2, H4, H6. So this one, again, is not simple because there are multiple outcomes. So this one is not. Moving on. Identify simple events again. Determine the number of outcomes for each event. Then decide whether it is simple or not. Explain your reasoning. For quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective part, machine part. So event A is selecting a specific defective machine part. So this would be a simple event because you're only selecting one, a specific, infers one. There is one outcome, and that outcome is a defective part. Number 2 says you roll a 6-sided die. Event B is rolling at least a 4. So now we have the words at least a 4. So at least 4 means we could roll a 4, we could roll a 5, or we could roll a 6. Since we have 3 different outcomes, this is going to make this not a simple event. Based on the fact there are 3 possible outcomes. Okay. Next is the fundamental counting principle. And the fundamental counting principle allows us to determine how many ways an event can happen. So if one event can occur m different ways, and a second event can occur n different ways, the number of ways the 2 events can occur in sequence would be m times n. So you're going to see this a lot as we go through this next couple of sections, where we talk about how many different ways things can happen. So for example, you are purchasing a new car. The following manufacturers, car sizes, and colors are listed below in the table. You can choose a Ford, a GM, or a Honda. You can choose a compact or a mid-size car. You can choose white, red, black, or green. And so here's your diagram. And as you can see, the diagram gets a little more extensive. But here's your Ford, your GM, and your Honda. Then you could get a compact, a mid-size in each one, and you have the 4 different colors. So you could get a Ford that's a compact that's white. You could get a Ford compact that's red. You could get a Ford mid-size that's green. So each one of these is options. Well, rather than have to do a tree diagram in every case, we can use the fundamental counting principle, and that will allow us to get the information. I often call these slot problems because there are 3 choices. The first choice is the make, then we have the size, and then we have the color. We're going to multiply those together. How many different manufacturers? Well, we have 3 different manufacturers. We have 2 different sizes to pick from, and we have 4 different colors. When I multiply those together, 2 times 3 is 6, times 4 is 24. We have 24 different car options. 24 different car options. And if you were to count this bottom row, 1, 2, 3, 4, 5, 6, 7, 8, another 8, and another 8, then that would give you the 24. If I'm interested in seeing them, then obviously a tree diagram helps. If I don't need to see what they look like, and I just want to know how many options there are, then we would multiply those together. This is also often the case whenever they talk about how many different ways you can order a Subway sandwich, how many different ways you can order your hamburger, how many different toppings are there on a pizza. So it can tell you real life sort of how many different options. And oftentimes in commercials you may have heard that. So using the fundamental counting principle, the access code for a car security system consists of 4 digits. Each digit can be any number from 0 through 9. So any number 0 through 9, that's actually 10 choices. So be careful there. You actually have 10 choices, 0 through 9. So how many access codes are possible when each digit can be used only once and not repeated? So again, we have 4 slots. I'm going to multiply those together. Each digit can be used only once. So that tells us that we have 10 choices for the first one, 0 through 9. But in the second slot, I can't use whatever I chose for the first one. So there would be only 8 choices. In the third slot, I can't choose what I picked for slot 1 or for slot 2. So for slot 3, there's only 8 choices. And then likewise for the last position, there's only 7. If we multiply this together, that would be 5,040 choices. And so again, we're talking car security. That's a lot of different combinations that a thief potentially would have to run through to determine what your password looked like. And that's if they cannot be repeated. If they can be repeated, then again, we still have 4 slots. We're still going to multiply, but each digit can be repeated, so there are 10 digits to choose from for the first slot. However, in the second slot, I still have 10 choices. In the third slot, I have 10 again, and in the last slot, I also have 10, because I can repeat. So in the first example, if I used 4 in the first case, I couldn't use 4 again. In this case, if the first number is a 4, I can use 4 again. And if I multiply those together, I would end up with 10,000 choices. Then we can get a little bit more creative and we can say, okay, each digit can be repeated, but the first digit cannot be 0 or 1. So we still have 4 slots. Still going to multiply. The first digit, so this would be our first digit, cannot be a 0 or a 1. So instead of having 10 choices here, I only have 8. Because they can be repeated, then I can have 10 choices here. No restrictions on that second digit. No restrictions on the third digit. No restrictions on the last digit since they can be repeated. If I multiply these together, then I have 8,000. This is very common to see again. Oftentimes commercials will even show you how many choices you have. Okay. Then we're going to talk a little bit about different types of probability. We have the theoretical probability, which is also called classical. And it's used when each outcome in a sample space is equally likely. The classical probability for an event is given by the number of outcomes in each event divided by the number of outcomes in the sample space. So now we're talking about probability of an event. Not just that the event happened, but what's the probability. So we do need to know how many outcomes. So just like we did here, we knew how many outcomes there were whenever you roll the dice. Now I want to know what's the probability of getting these numbers to show up on the die. What are my chances that they're going to come up? And that's classical or theoretical probability. So you roll a 6-sided die. What is the probability that you roll a 3? What's the probability that you roll a 3? So that's going to look like the probability of a 3. How many outcomes are there for this event? How many different outcomes are there when you roll a 3? Well, there's only one. There's only one 3 on that 6-sided die. They don't repeat. How many possible outcomes? There would be 6. So the probability that you roll a 3 is 1 out of 6. So what's the probability then that you roll a 7? Well, again, if you're looking at a 6-sided die, typical standard 6-sided die, the sample space would be you roll a 1, a 2, a 3, a 4, a 5, or a 6. There is no 7. So the chance that you're going to roll a 7, the probability that you're going to roll a 7 is going to be, there's no 7, there's none. No 7 in my sample space. There are 6 options only. So 0 divided by 6 would be 0. You will never roll a 7 on a 6-sided die. Okay. How about the probability that you roll a number less than 5? So if we're going to roll a number less than 5, well, that would be a 1, a 2, a 3, or a 4. These are the numbers less than 5. So the probability that your number is less than 5 would be 4 out of 6, which is equal to 2/3. Statistical probability is also called empirical. Probability. And this is based on observations obtained from probability events. The empirical probability of an event is the relative frequency divided by the total frequency. So this is going to be more when you're surveying people, or when you're doing things where you don't have the exact number, but you're using data or you're using statistics to get you the probability. So, for example, a company is conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. The pie chart below shows the results. What is the probability that the next adult surveyed read only print books? So what's the probability that they read print only? So in order to find that out, again, we're having to base it on some data that's already known. That's what's going to make this empirical. This is the data that we've collected. So we're going to make an educated guess on what the probability would be. So the probability that they read print only would be, now how many read print only? So read print only books was 578. Out of how many were surveyed? Well, it tells me there were 1,490 surveyed. So 578 divided by the 1,490, it's going to be approximately 0.388. You're going to be needing your calculator a lot in these because we do want to have approximate answers often. All right. So another example, a company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 have been surveyed. The frequency chart shows here below, or to the right. what is the probability that the next user survey is 23 to 35 years old? So what's the probability that the next person that is surveyed is that age? Well, based on previous survey results, then so far, the ones that are surveyed, there's been 312 in that category. So the probability that they are aged 23 to 35 would be the 312 divided by the 975, which this time it's an equal number, and equals 32.32. So there's about a 32% chance that the next person that's surveyed is going to fall into that group. Obviously, there's going to be a lot less probability that they would be 65 or older, because that's the smallest group that's already been surveyed. So one of the things that we're also going to do to help us with this probability and determining how we get answers is going to be what's called the law of large numbers. So that says if an experiment is repeated over and over, the empirical probability of an event approaches the theoretical probability of the event. And this is often the case whenever we talk about something just as simple as tossing heads or tails. So you know if you have a coin that when you flip the coin, it's either heads or tails. So the theoretical probability then is probability of getting a heads would be 0.5. The probability of getting a tails would be 0.5. But if I gave everybody a coin and told you to flip it 10 times, the chances that you got exactly 5 heads and exactly 5 tails would not happen very often. You can try it on your own, but the chance that it happened exactly 50-50 is very slim. If you did the experiment 10 times, or you had 10 people flip a coin 10 times, the chances of them getting exactly 5 heads and 5 tails individually may be nowhere near 50-50, but now you flipped it 100 times because you had 10 people times 10 flips. So now you have 100 flips of the coin. And the more flips and the more tosses of that coin that you get, you will have the likelihood that you will get this 50-50 range. And so that's what this is showing you. The number of tosses when you first start out could really dictate a really change in the probability. But over time, the more you do this, the more that this levels out and does indeed become more like the probability. So that's the law of large numbers. Basically, it says the more the experiment is done, the better or the closer the probabilities become. So that's important because now when we look at things, we can then have empirical and theoretical probability merge. And that's important when we're talking about predictions and what's going to happen next and what do you think will happen and how will that happen. So the next type of probability is called subjective probability. And this is a result from intuition, an educated guess, maybe estimates. And so this is where we talk about patient's health a lot of times. So a doctor says that you have a 90% chance of full recovery. Well, you know, he's going to base that on his experience with this type of surgery or this type of injury. So a business analyst may predict the chance of an employee of a certain company going on strike is 0.25. Well, again, that might be that he's seen and worked with this type of company. They've gone on strike before. How often have they gone on strike? What is his intuition? What's his estimated guess? This is very much the case on weather. And so when you talk about what the chance of rain is, well, they're using an educated guess based on data, based on the same predictions that have happened in the past, based on the weather conditions, the wind shear factor, all of that. It's all the same predictions, but it's still sort of their intuition and an educated guess as to whether or not it's going to rain. And also, it may be a 90% chance of rain and never rain in your area, but it may rain down the street. And so a lot of that has to be factored into it as well. So classify the statement then as classical, empirical, or subjective. So the probability that you get an A on your next test is 0.9. Well, this one would be subjective. How do you know you're going to get an A on your test? Well, if you've gotten A's on all your other tests, then that might be a good indication. That might be a good guess. If you've studied hard for this test, that might give you that edge on making an A. But it is subjective. It's up to you on whether or not you can make that A. So it's very subjective. But you're also using data to support that subjectivity. Number 2, the probability that a voter chosen at random will be younger than 35 years old is 0.3. Younger than 35. This is going to be empirical. And if you go back up to the definition of empirical, empirical then is based on a randomly selecting survey kind of things that are statistical probability. It's based on frequency, how many people have been surveyed, the frequency that happens. The probability of winning a $100 raffle ticket with one ticket is 1 out of 1,000. And this one then would be classical. 1,000 tickets were sold, only one is a winner. So the probability that you win is 1 out of 1,000. And that would be classical. All right, so by now you may be looking at or thinking about how does probability fit into the chances, the predictions. Well, it says probability of event E is always going to be between 0 and 1 inclusively. So that says that between 0 and 1, that's where your probabilities should lie. So if you get a probability greater than 1, you're in trouble. If you get a probability that's a negative number, you're in trouble. All of them are going to be between 0 and 1. And if we think of this like percentages, then it's going to be between 0 and 100%. You can't have the probability that something's going to happen greater than 100% or less than 0%. It's impossible to happen if it's a 0. And this was like the probability that we rolled a 7, if you remember. There's no 7 on a 6-sided die, so that's an impossible answer. So the probability is 0. The probability of 1 is certain if it is going to happen without a doubt. So in other words, what's the probability that you flip a coin and you get heads or tails? Well, that's the only two choices you have. You're not going to get, only heads or only tails. It'll be both. That's certain to happen, unless it's a fixed coin. All right. So then some other things that will help us as we're clearing up probability. The first one is complementary events. And complementary events will allow us to figure things out by maybe looking at it in reverse, maybe thinking about it the opposite way. So the complement of an event is the set of all outcomes in a sample space that are not included in the event. So it's the chances that it's not still in the sample space. So this is the event. This is the event. This would be outside here, would be everything not in the event. But since we know that the probability at most can be 1, then this tells us we have this formula, probability of the event plus the probability of the complement of the event. And we say E naught, so not the event. If I put these together, knowing that together they can't be greater than 1, then those two together will equal 1. The probability of the event plus the probability that the event does not occur has to equal 1. What's important, though, is whenever I look at it in a little different light, the probability of the event by itself would be equal to, I'm doing a little algebra here, if I subtract the complement from both sides, I would get the probability, I would say the probability then of E would be equal to 1 minus the probability of the complement. Likewise, I could also subtract the I could also subtract the P of E from both sides. And then I could say that the complement, the probability of the complement would be 1 minus the probability of the event. So both of these formulas then will help you when you're determining what and how to find that answer. They are connected. And because they can't be greater than 1, then by subtracting it from 1 makes it a whole lot nicer. So for example, find the probability of randomly selecting a social network user who is not between 25 and 35. Who is not. Now there are two ways. There are two ways. So the first way would be to say, what's the probability that they are 18 to 22 plus the probability that the person is 36 to 49 plus the probability that they are 50 to 64 plus the probability they are over 65. So they are greater than 65. So that's not terribly hard to do whenever you look at it that way. The probability that the person is 18 to 22 would be 156 over 975 plus the probability that they are in the 36 to 49 group would be 254 over 975. The probability that they're in the next group would be 195 over 975. And the probability that they would be over 65 or 65 and older would be 58 to 975. If I add all these together, I would get 663 over 975, which is exactly equal to 26. So that's not terribly hard, but remember we only have 4 categories that are not the one we want. Remember, this is the one we want, or don't want in this case. So there are 4 categories that we do want. What if there were 20 categories that we wanted and only 1 we didn't want? Well, then doing this way could take a little longer versus the second way, which would be to say the probability that we don't pick that range. So the probability that we don't have, they are not 23 to 35, would equal 1 minus the probability that they are 23 to 35. So from a previous example, we knew that the probability that they are 23 to 35, So the probability that they are 23 to 35, we determined was, again, 312 over 975, which we determined was 0.32. So the probability that they are not that age, then would be 1 minus the 0.32, the probability that they are, which is equal to 0.68. So this second method is much easier whenever you consider how many categories you might have or how you can determine it. It's much easier to determine one probability and then subtract than it is to try to figure each individual probability out. And you will see that used a lot. All right. So this next one's going to be to use a tree diagram. It says the probability experiment of tossing a coin and spinning the spinner shown to the right, where they're equal likely to land on each number. Use a tree diagram to find the probability of each event. So event A is tossing a head and spinning an odd number. Event B is tossing a head or spinning a number greater than 3. So let's get our tree diagram going first. So we have heads and we have tails. From that heads or tails, we have the numbers 1 through 8. 1, 2, 3, 4, 5, 6, 7, 8. Likewise for tails. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8, not 8, 7. Not sure where that comes from. Okay. So now my exact sample space would be, I'm interested in the sample space, would be H1, H2, H3, H4, H5, H6, H7, H8, then tails, so tails in a 1, tails in spinning 2, tails in spinning 3, tails in spinning a 4, tails in spinning a 5, tails in spinning a 6, tails in 7, tails in 8. So how many options do we have? How many outcomes? Well, we would have 1, 2, 3, 4, 5, 6, 7, 8 for flipping the head, and another 8 for the tails. So there would be 16 outcomes. 16 outcomes. So now let's read the question carefully. The event is tossing a head and spinning an odd number. So what is the probability that we get a head and odd? So if I look at my sample space, head and odd. So this would be a head and an odd number. This one would be a head and an odd number, head and an odd number, head and an odd number. So in this case, there would be 4 outcomes, 4 positive outcomes, 4 that we wanted to happen, out of 16 total outcomes. So 4 divided by 16 would be 1/4, or 0.25. For the B part, or the second part, this one is going to be tossing a head. Oh darn. For this one here, this would be a head. It doesn't change the outcome because heads and tails are the same. But let's make that correct. Sorry. All right, so this one says tossing a head or spinning a number greater than 3. So tossing heads or spinning a number greater than 3. So tossing heads would be all of these. Doesn't matter what the outcome of the number is because I tossed a head. Then the probability that I spin a number greater than 3, well, the 4, the 5, the 6, 7, and 8 are all greater than 3, but I already counted those because I flipped the head. So all I have to do now is include all of the numbers greater than 3 when I do a tail. So that would be this one, this one, this one, and this one. Oh, greater than 3 also includes the 4, sorry. So this time I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 outcomes that fit that event divided by the 16 total, and that's going to be approximately 0.83. All based on the difference in the word and the word or. And we're going to see more of that very soon, but that is going to be very important, that word and or the word or. All right. When we're in class, I'd be asking, do you understand? Do you have any questions? All right, last question. Using the example regarding access codes from above, find the following probabilities. So we're going back to the access code problem that we did, which if you remember at the beginning of the lesson, those were what we called slot problems. So the first one says, find the probability of correctly guessing the access code when each digit can be used only once and not repeated. So if you remember, I'll just do the first one. We had 4 choices. They could not be repeated. So the first option is 10, and then 9, and then 8, and then 7, and I multiply that together. We were given 540 different values. So the probability that you correctly guess that code, the probability that you guess it correctly, there's only one correct code, one correct guess, so that would be 1 over 5,040. So not very often will you guess it, so the probability that you are going to guess incorrect is more likely to happen, because incorrect guesses would be 5,039 incorrect guesses. Okay. So 5,040. I am going to show you this on the calculator, because when you do this on the calculator, you're going to get scientific notation. So we do want to talk just about that real quickly. So 1 divided by 5040 is equal to, here's this very ugly number, 1.984126984 e to the negative 4. So it's this e to the negative 4 that we need to talk about. So it was 1.984126 something, something, something. And then you had e negative 4. That number doesn't make sense to us until we put it out of scientific notation and into decimal notation. What the scientific notation is telling us to do is to take this decimal point, and we're going to move it because it's negative. We're going to move the decimal point 4 places left. Sure, move that down. I don't think I can. We'll just make it work. So 4 places to the left. So right here is my decimal point. 4 places to the left. just going to put my decimal point right here, and it's going to add 3 zeros. So my answer here is 0.00019841, which we will round to approximately 0.000198. You'll have to look in your MyMathLab and look on your stuff to tell you what to round the decimals to. Sometimes it says to 3 decimal places, sometimes it might say to 6 decimal places. You'll have to read what your problem says. So again, the second one, what was the probability of correctly guessing whenever you had the access code? Draw the tool back up. Looks like it's not reading it. Right. So correctly guessing So the probability that we guess correctly for the access code when each digit could be repeated. Well, again, if we go back up to the first example, we would see that that was 1 out of 10,000. Because this time the codes could be repeated. And 1 out of 10,000, again, gives us the 1e negative 4. Remembering that the decimal point for this one is right here. So again, if I move it 4 places to the left, you end up with 0.0001. That is not an approximate answer. It is an actual complete answer. So it's not approximate, it's exact. So this time you would not round. When they're exact, you want to keep them non-rounded if at all possible. Unless, again, they tell you in MyMathLab, so just be careful. So the probability then of not correctly guessing when the access codes, when each digit can be repeated. Now, what's the probability? Well, that would be 1 minus the probability that you did guess correctly. So the chances that you didn't was 1 out of, we can do it one of 2 ways, 1 minus 1 over 1,000, or 1 minus 0.0001, which is equal to 0.9999. So obviously, the probability that you're not going to guess that code correct is very high. The probability that you will guess that code correctly is very low. So you're going to see this not show up a lot. All right, and that wraps up section 3.1.